Hello, everyone. I'm Pengtao Xie, assistant professor from UC San Diego. Today, I'm going to talk about our recent work training highly generalizable biomedical image segmentation models with very few annotations. This is joint work with my PhD student, Li Zhang. So biomedical image semantic segmentation is a fundamental task in healthcare and biology. Basically, the task is we have our input image, and we want to predict the semantic segments in the image. We label each pixel in the image with a semantic label. For instance, here the input is MRI image. The output would be something like this. So basically, we label the different regions in the brain using different classes. It has many applications in healthcare, medicine, biology, etc. Nowadays, the semantic segmentation is mostly conducted using deep learning models, which has demonstrated very strong performance. Some of the notable models include the UNet, DeepLab, and recently the SegFormer. The problem of these models is that they need to be trained with a large amount of labeled training data. Basically, the input image and the output segmentation mask. And the output has the same size as the input. Labeling these segmentation masks for biomedical images is very challenging. First of all, it requires very strong domain expertise. Only physicians and also biologists can do this kind of labeling. It's different from the general domain that you can hire many workers from Amano AMT to do the labeling. But here for the biomedical images, only a small group of experts can do this. And also the objects in these biomedical images are very complex. For example, here we have this brain. There are so many different areas. Right? It's very time consuming to do the labeling. And also labeling these segments is pixel-wise. Basically, for each pixel, we need to give a label. And for biomedical images, as you know, the resolution typically is very high, right? Thousands by thousands of pixels. It's very time-consuming and labor-intensive to label these millions of pixels in a single example. So to address this problem of lacking of labeled data, there are many different types of methods. Roughly, they can be categorized into two categories. The first one is data augmentation. Basically, we take this human-labeled real image, then apply these different augmentation methods like rotation, flipping, etc. to create some augmented images. The problem of existing data augmentation methods is data augmentation and the training of the semantic segmentation model on the augmented data is separated. Basically, we first augment the data. After we get the augmented data set, we train a model. Right? So these two tasks are separated. And when we do the data augmentation, it has no guidance from the semantic segmentation performance. As a result, the augmented data may not be suitable for improving the segmentation models. Right? We do something that we thought might be helpful, but actually when it is applied to train the model, it does not. The other type of methods are the semi-supervised learning methods. So basically, we have a small set of labeled images, but we have many unlabeled medical or biology images. So we develop semi-supervised learning methods to combine this labeled and unlabeled data together and do the learning. The problem of semi-supervised learning is that it requires external unlabeled images. Maybe this is easy to get in the general domain. Right? You can get millions of images from Flickr or some other public websites. But in the biomedical domain, even for the unlabeled images, they are difficult to obtain. For instance, if it is medical image, we need to go through the IRB process, which is very time-consuming and expensive. There are many privacy concerns. And for the biology images, they are very expensive to acquire. Right? We need to run the equipment to acquire some images, which is very expensive and also time-consuming. Right? In certain cases, acquiring one image can take several weeks. So we basically want to develop a unified method to address the limitations of existing methods. At a high level, our method performs data augmentation and the semantic segmentation model training end-to-end. Basically, we leverage the performance of the segmentation model to inform the data augmentation process, right? To tell the augmentation model what kind of data is needed. And our method does not require external data. What we have access to is just the dataset, a few labeled images for the semantic segmentation task, and that's all the data we have access to. We don't need any external unlabeled images. And this is also a general framework. It is developed to improve different kinds of semantic segmentation models, no matter it is UNet or SegFormer or DeepLab, etc. Right? They can be all plugged into this framework and get input. So it is agnostic to the different segmentation models. So this is an overview about this method. It has the following steps, which are organized into a loop. First of all, we train, so in the framework, we have two models. One is a data augmentation model. The other is a semantic segmentation model. So for the augmentation model, it has two sets of learnable parameters. One set is about the weight parameters. The other set is about the architecture, neural architecture of the model. So in the first step in this workflow, we train the weight parameters of the augmentation model and tentatively fix the architecture. Then given this trained model, we utilize it to generate this augmented image segmentation mask pairs. Then given this augmented data, we use them to train a semantic segmentation model together with a few human-labeled real images. Then we validate this segmentation model on another validation set. And this validation performance basically reflects how good this augmented data are, right? So if the augmented data is bad, then you use it to train a model, the performance of the model is going to be bad. Right? So we can basically leverage the validation performance of the segmentation model to tell us how can we improve the augmentation model to generate better augmented images. Right? So in the last step, we basically update the architecture of the augmentation model to minimize the validation loss of the segmentation model. Okay, so this is how the data augmentation is conducted. So we basically take a reverse approach. The forward process is we have an input image, medical image, and we want to predict the segmentation mask. Then we reverse this process. So we take a human-labeled original segmentation mask, then do some basic augmentation operations, such as flipping, rotation, translation, etc. Then we get some augmented masks. And then we train a deep generative model, which takes a segmentation mask as input and generate an input image. So this is a mask to image generation model. Right? The input is an augmented mask, and the output is an augmented image. Right? So after this step, we basically get a pair, right? Where the input is an augmented image, the output is an augmented mask. And we can repeat this process as many times as you want and get a large augmented data set. So next, I'm going to talk about the mathematical formulation of this framework. So we basically have three stages, which are conducted jointly in a multi-level optimization framework. So at the first stage, we train a mask to image generation model. So this is a GAN-based optimization problem. So the DGAN means the data utilized to train the GAN model. So this data set, DGAN, is essentially the same as the semantic segmentation data set. Right? In a semantic segmentation data set, we have the input image and output mask. We basically switch their order, right? Where the input is the mask, output is the image. Then we use this to train the GAN model. So G here is the weight parameters of the generator. D here are the weights of the discriminator, and A is the architecture of the generator. A is also learnable. So we solve this min-max problem. We minimize this loss, the loss of the GAN model by with respect to the generator, and also we maximize this loss with respect to the discriminator. So at this stage, this architecture of the generator is tentatively fixed. Right? So after resolving this problem, we get the optimal generator G star, which is a function of the architecture, right? Because A is not optimized here. Each time you have a different A, you will have a different loss function, and the optimal solution of G star, the weights of the generator would be different. So it's a function of A. Okay, after we train this model, we are going to use it to generate these augmented images. As we described earlier, given a real segmentation mask labeled by the human, we first do some basic data augmentation to get some augmented masks. Then we feed those masks to this trained generator in the GAN model, G star A, to generate the input image. Right? Then the input image and also the mask form this augmentation data set denoted by DAUG. Right? DAUG, the input is the real data provided by human. We do the augmentation using the generator containing the weights and also the architecture. So this is augmented data set. Then we can use it to train a semantic segmentation model, W here. It can be any model we like, UNet, DeepLab, etc. So this is the segmentation loss here. And meanwhile, we can also train this model on the human labeled dataset, dtrain, right? Then we add these two losses together. Lambda here is some trade-off parameter. Then we minimize this loss to train the segmentation model W. Then the optimal solution W star would be a function of G star A and A, right? Because again, because A is not optimized yet, so each time A is changed, we are going to have a different loss function here, and the optimal solution would be different. And in the final stage, after we get this segmentation model, we basically evaluate this model on a human-labeled validation set. So DVAL is a human-labeled validation set, right? So this is basically the validation loss. And this loss is a function of the architecture of the generator A, right? And this loss basically reflects how good this architecture is. Right? If the loss is large, that means the generated data has low quality. And then that means the architecture of the generator is not very good. Right? So we can improve the architecture A by minimizing this validation loss. Then we can put all these pieces together and we get this multi-level optimization-based formulation. So it has 3 levels here. The output of the first level would be the input of the second level, and the output of the second level is the input of the third one. And at the third level, we optimize the architecture A. After A is optimized, the loss function in the first level is going to be changed. Right? So we redo this process. So it's in a loop. The 3 stages are in the loop. They are mutually dependent on each other. By solving these 3 problems together, we can basically do the end-to-end learning of the 3 stages and do the end-to-end learning of the semantic segmentation and also the data augmentation to make sure the augmented data is specifically useful for improving the segmentation model. Okay, now I'm going to present some results. So we conducted experiments on 2 tasks. One is the skin lesion segmentation from dermoscopy images. So here we have 3 data sets. On ISIC, we have a training data set and a test set. The model is trained on the ISIC training data set. When we do the evaluation, do the testing, we test not only the in-distribution performance. In-distribution basically means the test and the training data are from the same data set, ISIC. We also evaluate the out-of-distribution performance. The out-of-distribution is conducted on PS2 and the DERM-IS. The other task is lung segmentation from chest X-rays. We also have 3 data sets and evaluate both the in-distribution and out-of-distribution generalization. So here are the results for the skin lesion segmentation. So here, ISIC means, so this part is the data set for training. This part is the data set for testing. So basically, test data and the training data are in the same distribution coming from this ISIC data set. But they are different. There is no overlap, of course. So here in this figure, the x-axis is basically the number of training examples. We take 40, 200, and 20 to train this model. And the y-axis is the G-card index to evaluate semantic segmentation. The higher, the better. Then for these dots, there are different methods. Let's compare these two. So this red diamond, which is our deep lab, basically means we apply our framework to deep lab, plug deep lab as W into our framework. And this green box is the vanilla deep lab, basically the vanilla deep lab trained without using our framework. We can see that our deep lab and this vanilla deep lab have similar performance, around 76%. But for our method, we only need 40 training examples. And for the vanilla deep lab, it needs 2,000 training examples. So basically, we can reduce the sample complexity by 50 times without losing the performance. And similarly for UNet, so this is a vanilla UNet, this blue circle. It needs 2,000 training examples. And for this triangle here is ours UNet. It actually achieves better performance than the vanilla UNet with 50 times less training examples. Yeah, so this basically demonstrates that our framework has this capability to train highly generalizable semantic segmentation models using a very small amount of labeled data. Instead of labeling 2,000 by the doctors, we can just label 40 and then apply our method. We can achieve a performance that is similar to 2,000 examples. Here are some evaluation on out-of-domain generalization. So ISIC here is the training data. PH2 here is the test data. They are from different distributions. And similarly, for this plot, the test data is DERM-IS, which is in a different distribution from ISIC. We can see that similar to the previous figure, so this diamond is our deep lab. This blue box is deep lab. We can see that our method achieves similar performance as vanilla deep lab, but with much fewer training examples, 40 versus 2,000. And similarly here, we also observe strong generalization performance. Yeah, these are the results on the lung segmentation. The observations are similar to the previous ones. We also compared with other augmentation baselines, including rotation, translation, flip, and their combination, etc. So this green bar here is our method, and it outperforms these baselines significantly. In our framework, we do this all the 3 stages end-to-end by using multi-level optimization. You may wonder whether this end-to-end is indeed helpful. To check that, we basically break these 3 stages into 3 separate stages, basically do them step by step separately. And this would be the performance. This blue bar here, we can see that after reducing from end to end to separately, the performance suffered a great drop. So this basically demonstrates that it is indeed helpful to do this end-to-end learning so that the segmentation performance can inform the augmentation process to generate augmented data that is specifically useful for improving the segmentation models. Here are the comparison with augmentation baselines on the lung segmentation, whereas the observation is similar to the previous one. We also compared with the semi-supervised learning baselines, and in these baselines, they have access to many unlabeled images, as many as 100,000. And in our method, we don't use any unlabeled data. As we can see that our method actually outperform these baselines in certain cases, or achieve similar performance as these semi-supervised learning baselines, which requires many unlabeled images that are difficult to obtain in biomedical domains. Here are the comparison on lung segmentation, where the observations are similar. Here are some qualitative examples. So the model is trained on the GSRT dataset and tested on GSRT, NLM, and SD. So for the second row, it's an out of distribution generalization problem. We can see that when this test image is out of distribution, basically it is scaled right to this upper left region. These different methods, these guys, deep lab, and also these semi-supervised learning methods, basically fails on this example. And our method can successfully recognize these lung regions, even when this test image is quite different from the training images. Here are some data augmented by the framework. So these are the augmented masks, and these are the correspondingly generated input images. We can see that the generated images, the lung regions, aligns very well to the segmentation mask. So to conclude, we propose a general framework which conducts data augmentation and semantic segmentation end-to-end. To achieve this goal, we build a multi-level optimization-based framework. The advantage of our method is it does not require any external unlabeled data, and it is a general framework that can be applied to improve different semantic segmentation models. And in the experiments, we show that our methods can achieve very good performance with fewer training examples, and it can generalize for both in distribution data and out of distribution data. So I guess I have maybe 2 or 3 minutes. I also want to briefly mention about something that is general. So what I discussed is basically a special case about a more general project that my group has been working on in the past 3 years. It is called Skillearn, basically a general framework that leverages the inspirations from human learning to get some training strategies for improving machine learning models. So I'm going to skip the goal here is we want to develop some training strategies to improve the performance of the machine learning models without designing new models or collecting more data. So basically here, this is a multi-level optimization-based general formulation. we emulate the different learning stages in a human learning technique, such as learning by self-explanation, active recalling, etc. And all these different stages are conducted end-to-end to achieve the overall best performance. So for the example that I just presented, it's actually inspired by reverse thinking, right? So in the normal thinking, we have an input image, we want to get the segmentation mask. Then the reverse thinking is basically about given a segmentation mask, can you guess what would be the input image? Right? How does it look like? That's how it is leveraged to do this reverse augmentation. So we can basically take our general scalar framework and instance it to this reverse segmentation framework that I just described by mapping the elements in this scalar framework to these specific objects in the segmentation work I just discussed. Here is a summary about what we have done so far. So at the core of this project, we developed this scalar framework. The goal is to develop machine learning training strategies inspired by human learning skills. It is based on multi-level optimization. So for this work, it was recently accepted by ICML. And to support the development of this framework, we built a system called Betty. It is a programming framework for multi-level optimization. So users only need to define the multi-level optimization problem. Then in the backend, the system is going to automatically solve it, kind of like PyTorch, but with support for multi-level optimization. Then on top of this scalar framework, we develop the instances. So for each instance, we take a human learning technique, such as learning by self-explanation, small group learning, etc., and use this framework to transform it into a machine learning training strategy that can be applied to improve different machine learning tasks, such as neural architecture search, data reweighting, augmentation, etc. Then on top of these improved tasks, we develop healthcare applications in medical images, medical dialogue, visual question answering, etc. With that, I am going to conclude here, and thank you for your attention.